Hello everyone, welcome for this second session of electronic devices. So in the last session we have discussed about the basics of the particles, the basics of the Bohr model and the postulates of it, and we also seen the various series like Lehman series, Balmer series and Paschen series, and we have also seen the limitations of the Bohr model, why it is failed to represent that to the higher atomic numbers. And that is why we are going to see in this tutorial the wave particle duality, because the atom can be act as the wave as well as the particle. It has a dual property nature, and also we will see the quantum mechanics, how it is very important. So now let us switch to our screen, and we'll see that. Okay. Now, when we talk about the wave particle duality, we know that the electromagnetic radiations has the dual nature. So, the electromagnetic radiation has the dual properties. That is, it can act as wave. The electromagnetic radiations can act as wave, and at a times it acts as a particle. So it can act as a particle. So the wave theory of light is quite satisfactory for long waves used in the radio communications. Means when we talk about the low frequency signals, so if the wavelength is very long, so low frequency in the sense, so if I write the waveform here, so what happens, these are called as the long waves, because the wavelength, if we measure from one peak to other peak, the distance between these lambda, the wavelength, is very large. So it has the larger wavelength. So it has the larger wavelength. And when we talk about the short wavelength radiations, it means we are talking about the high frequency signals here. So these are the high frequency signals. So when we measure the distance between these two peaks here, that is the lambda, is very less. So these are called the short wavelength radiations. So these short wavelength radiations, in these short wavelength radiations, these electromagnetic radiations acts as particle, whereas here in this case it acts as waves. So basically all the radio frequency uh, range spectrum, we can consider the electromagnetic radiation as the waves, and whereas the ultraviolet and visible light, whereas the visible light frequencies which has very high frequency, and the ultraviolet frequency range or the region of the spectrum, we can call these acts as the particles. These acts as the particles. Okay. So these particles is nothing but we call it as it has certain energy with okay. So when we call this as the particle, so these are nothing but the photons which has certain energy. So these are photons which has an energy of h into nu. Okay, so this is the energy, and a photon always travels with the velocity of light, as we all know, and will not exist at the same velocity lower than that of the light. It means that the photons travels with the velocity, with the same velocity of the light, whereas the lower frequencies will not be traveling with the same speed. So therefore we can say that these photons doesn't have the rest mass. So because the potential energy we cannot consider here, so it doesn't have the rest mass. And like protons, even electrons also has the dual nature. The electrons also has the dual nature, and besides not just the electrons, like heavier particles such as the protons, neutrons, and neutron atoms or molecules uh, shows the wave-like behavior. Means the heavier, if you look into the heavier particles, that is the heavier particles are the protons, then neutrons, it or molecule, so it represents the wave-like behavior. So it represents the wave-like behavior. So to understand this, so wave theory is proposed by Louis de Broglie in 1924. So sorry, Louis de Broglie has proposed the wave theory, has proposed the wave theory in 1924, and he shows the particle of momentum p has a behavior. He suggested that the particle of momentum p shows the wave-like behavior with wavelength. So what does he suggested that? So he suggested that a particle of momentum p shows wave-like behavior with the wavelength lambda is equal to h by p, or this can also be written as, sorry, not and, so this can also be written as lambda is equal to h by m into v. So if you look into this equation, so here the h is nothing but the Planck's constant. So this is the Planck's constant, and p is the momentum of the electron, and here into this equation, if you see, the h is again the Planck's constant, and here m represents the mass of the particle in kg. So this is the mass of the particle in kg, and the v represents the velocity of the particle in meters per second. So it is the velocity of particle in meters per second. So the value of this Planck's constant is given by 6.626 into 10 to the power of minus 34 joules per second. So this is represented as Planck's constant. So now with this wavelength theory, we can say that the Broglie has stated that the wave-like behavior is exhibited only by the particles like electrons and protons that have small value of p because of their small mass. It means the wave-like behavior is exhibited by the electrons and protons that has the small value of, because it has the small value of p, that has the small value of p is nothing but the momentum, because of their small mass. Because these have the very small mass, that is why these particles acts as the wave. Whereas in the other case, if you look into, if the second case, if you see, macroscopic dimension objects have vanishingly small de Broglie wavelength, and their motion can be described by law of classical mechanics. It means the macroscopic objects, their motion is described by the classical mechanics but not with the quantum mechanics. So that is what it means. So the macroscopic object motion is defined by classical mechanics. Classical mechanics, not with the quantum mechanics, because as per de Broglie's theorem, or de Broglie's his presentation, it says that the macroscopic dimension has a vanishingly small de Broglie's wavelength. So now here there are certain questions that arises. The question is that now is the light is a wave phenomenon or a bundle of particles like photons? What is it? So the light is a wave phenomenon or it is a particle like photon phenomenon. And the second question is that is the electron a particle or a wave? So an electron is a particle or a wave. So these are the two questions which are in front of us. As of now, by looking the Bohr's postulate, the Neil Bohr's postulate, and by studying the de Broglie's wave particle duality, so we have two questions: whether the light is a wave phenomenon or a particle like photon phenomenon, and the electron is a particle or a wave. So to answer this, we have to understand the quantum mechanics. The quantum mechanics, or it is also called as the wave mechanics. Okay. So before discussing the quantum mechanics or the wave mechanics, let us take a small example here to calculate the wavelength by using the de Broglie's wave equation, by considering the mass of the electron and the velocity of that particle. So let us take a small example here. So let's take an example. So an example is given. So it is given like an electron has a mass of 9.11 into 10 to the power of minus 32, sorry, it is minus 31 kg, moves at nearly speed of light, moves at speed of light. So with using velocity, by considering the velocity as 3.00 into 10 to the power of 8 meters per second, calculate the wavelength, of the electron. So now we know the mass of the electron, so solution goes here. So mass of an electron is given by, so that is 9.11 into 10 to the power of minus 31 kg, so that is the mass, and the Planck's constant, we know it, that is h is equal to 6.6262 into 10 to the power of minus 34 joules per second, and the velocity v is equal to 3 into 10 to the power of 8 meters per second. Now the thing which we need to calculate is that what is the value of this lambda, the wavelength of this particle. So by substituting all these values into an equation, so we know that equation, that is de Broglie's equation, that is lambda is equal to h by m into v. So substituting all these values, so we will get the answer as 2 point, sorry, so we will get the answer as 2.42 into 10 to the power of minus 12 meters. So if you look at these solution, the wavelength. So wavelength is so small when compared to the diameter of the hydrogen atom. So it is just the 1/20th. The wavelength is very small, is about the 1/20th of the diameter of hydrogen atom. So with the looking at this equation, we can conclude that, so as the speed of the electron decreases, its wavelength increases. So it means if the speed of an electron increase, then let me not write the arrow mark, so then its wavelength decreases. Then its wavelength decreases. So that is what we can conclude with this example. Okay. So now let us talk about the quantum mechanics. So we'll first do a little comparison with the quantum mechanics with the classical mechanics, and then we will move ahead with the postulates, the basic postulates of this quantum mechanics. So let me write here the quantum mechanics. So basically there are three differences between the classical mechanics and the classical mechanics and the quantum mechanics. So what is the first difference? So classical mechanics deals with the macroscopic objects. It deals with the macroscopic objects, and it says that these objects are described in the infinite details. It deals with infinite details. So the first thing is that the classical mechanics says that it deals with the macroscopic objects, and these objects were described in the infinite details. It means, for example, to understand this very clearly, so it says these objects can move with any speed, and have any energy and can occupy any position in space. So that is what this classical mechanics says. It deals with the microscopic objects and it can have infinite details. So what is the meaning of infinite detail is that it means these objects, the macroscopic objects, can move with any speed and it can have any energy and can occupy any position in the space, and that is highly impossible with the quantum mechanics. So quantum mechanics, it disagrees with this statement, and it says the quantum mechanics, it does not support these hypotheses of infinite details. So it does not support this hypothesis. The hypothesis of does not support the hypothesis of infinite detail experience. So it does not support these infinite details, and quantum mechanics follows the postulates. It follows certain postulates. So this is the first difference between the classical mechanics and the quantum mechanics. So classical mechanics says an object can have any speed, any energy, and can take any position in space, whereas the quantum mechanics does not agree with this indefinite details. The second difference is that, so the classical mechanics deals with the number. It means every observation in classical mechanics, let me write as CM, provides number, and every analysis deals with number. Every analysis deals with number. It means anything it is done in the classical mechanics, it gives a very accurate results, very precise results, and it deals with the numbers. Whereas the quantum mechanics, it deals with the abstract notion. It means it doesn't give the accurate value, but it will deals with the physical meaning of it. So if you take an example here, so if you do the measurement of the measurement of volume of gas, so it gives us the number again. Either it might be a direct method or an indirect method. So whereas the quantum mechanics follow only the abstract, it follows the abstract notion or notation, abstract notations, and which may have the immediate physical meaning, and it has immediate physical meanings for it. And the third difference of the quantum mechanics is, classical mechanics is, the data is very precise. The data is precise. Means it precisely chosen, or it is precise. Just let me write as precise. Means any calculation is done, it is very accurate. But whereas in case of the quantum mechanics, these short predictions, it does not follow these short predictions because it violates the Heisenberg uncertainty principle. So the sharp predictions of observations, short prediction of observation is prevented by Heisenberg uncertainty principle. Uncertainty, maybe spelling is wrong, let me write clearly. Heisenberg uncertainty principle. Okay, and it also states that the pair of variables that are canonically conjugate to each other, uncertainty principle, which states that for any two pairs of the variables that are canonically adjacent to each other. So it means, so this theory of this short prediction cannot be applicable to a canonically, I'll tell you what is this canonical. It cannot be applied to this canonically conjugate variables. So So canonically conjugate variables means which are complement to each other. It means if you take the two variables where two variables cannot be true at the same time, only one of the variable value can be true at any given time. Whereas in case of the classical mechanics, they're very precise and tells when we talk about the two canonical, uh, it does not believe in canonical conjugate variables. It says both the variables uh, or means both the variable values can be predicted at the same time. So that is where the Bohr model has failed. So that we will talk later why it is failed, because the Bohr model has said an electron can have both the position as well as the momentum, and these values can be found at the same time. Whereas in quantum mechanics, it violates the principle of the Heisenberg and says the position and the position and the momentum cannot be defined at the same time because it violates. So these kind of variables we call it as the canonical conjugate variables. Okay, so canonical conjugate means which are complement variables. Okay, so now let us write what are these canonical variables. So these are the three differences. So basically let us have a quick revision here. So classical mechanics and quantum mechanics. So classical mechanics deals with the macroscopic objects, and it says it has infinite details. It means it can have any speed, any energy and any position at the same time. So whereas the quantum mechanics, it it does not support this hypothesis of infinite details, and it follows the postulates. And whereas the classical mechanics, the second is that every observation in CM provides the numbers and every analysis deals with numbers, whereas the quantum mechanics deals with the abstract notations and has certain physical meaning to these um, objects. And the classical mechanics gives the precise data accuracy for every measurement and calculations, whereas the quantum mechanics uh, you know does not support for this short predictions, because it violates the principle of Heisenberg uncertainty principle for canonical conjugates. Let me stress here, it violates for Heisenberg uncertainty principle for canonical objects. The canonical objects, variables, conjugate variables. So canonical conjugate variable means let me write it clearly. Canonically conjugate variables, it means the complement variables. Complement variables, it means the two variables cannot be true at the same time, only one of the variable can be true. So that is what it means, the complement variables. So now let us take the two pairs of the canonical conjugate variables. So let us consider two pair of canonical conjugate variable. So the first pair is momentum and position, and the second pair is energy and time. So these two are complement to each other. It means if an electron has a momentum, then we cannot define its position. If we define its position, then we cannot define the momentum of the electron. So likewise, the second canonical conjugate variables pair of variable is energy and time. If we define the energy of an electron, then we cannot define at what time, and if we define the time of that electron at what time, then we cannot define what is the energy of the electrons. So then let us write with the uncertainty principle that if delta x and delta p, so delta x is nothing but the position and delta p is nothing but the momentum. So delta x and delta p represents the uncertainty, represents the uncertainties in position x and momentum P of particle, momentum P of particle. I don't know, I'm making mistake in the spellings of particle every time. So particle, then it is given as, so we can write this as, then delta x into delta p is approximately equal to h by 2 pi. Let me call this as equation 1. So it states that the position of the particle precisely, if you want to locate the position of the particle very precisely by making this delta x equal to 0, then we cannot know, the momentum of particle, momentum of the particle, because delta p becomes infinite. Both cannot be infinite. So that is why this is the first comparison, as we have seen from the classical mechanics and the quantum mechanics. Okay. So if delta x becomes 0, then delta p will become infinite. So that is what it means. So similarly, if we see this with respect to the energy and time, so delta E, and if we consider the delta T, then by applying the uncertainty, if you apply the uncertainties in the measurement of E and T, then we can write, so delta E into delta T is approximately equal to h by 2 pi. Again, let us call this as equation number 2. So this is all about the wave particle theory and the quantum mechanics, and introduction to the quantum mechanics and the difference between the classical mechanics and quantum mechanics. So in the next session we will be talking about the postulates of this quantum mechanics. So there are 5 postulates. We'll talk this, and then we'll talk about the Schrodinger wave equations. Okay. So thank you for this watching this session.